Hello everybody, this is Rudra Pradhan here. Welcome to Engineering Econometrics. Today we will continue with modeling diagnostics, and that too discussion is on multicollinearity problems. In fact, in the last lecture we have discussed this particular component, and the issue is that it is the problem of linear relationship among the regressors. While regressing dependent variable with independent variables. So, one of the typical requirement is that independent variable should be linearly independent, but in reality with respect to real life problems, these independent variables are not actually completely independent. So, what is our target here? To check how how much the existence of relationship between or among these independent variables. So, that means technically we like to track out the degree of relationship among these independent variables. Whether it is low and high, it is not a issue, but it should not be statistically significant. The moment the particular correlation coefficient will be statistically significant, then the estimated model which is derived through OLS mechanisms may not be good to use to predict or the kind of or to forecast any kind of engineering problem. So, in order to knowing this particular issue, so let us start with the kind of component. So, this is a multiple regression problem. So, here we have a dependent variable and then we have independent variables. So, that means technically y is the dependent variables and then we have 5 independent variables. So, that means the issue of multicollinearity will be starting very at a high rate, you can say, or the complexity will start increasing the moment we will put one after another independent variables into the systems. So, ultimately this is a kind of problems where we have one dependent variable with 5 independent variables. So, that means we will have a different levels of relationship among the independent variables. Technically there are couple of pairs you will find starting with x 1, x 2, x 1, x 3, x 1, x 4, x 1, x 5, and similarly x 2, x 3, x 2, x 4, x 2, x 5, then x 3, x 4 and x 3, x 5, and finally x 4, x 5. So, ultimately, so this is how the kind of case. So, it is a 5 C 2 times you will find such relationships, and then out of all these relationships you will find some cases it is actually go against the model estimations, or some cases it may in favor of model estimation. For instance, you cannot say favor completely, but the technically the favorability of relationship or the favorability of the model will come into the pictures when the relationship among the regressions will exactly equal to 0, but in a real life scenario you will not find such kind of environment. So, anyway, so this is a problem. So, where y is the dependent variables and represents oil productions, and it is affected by couple of independent variables like US energy consumption. That means, technically and this oil production is at the world levels, total world oil productions, and it is affected by couple of independent variables. The first one is USA energy consumption, USA nuclear generation, USA coal productions, USA dry gas productions, and USA fuel rate for automobiles. So, that means technically means from this problem it is very much clear that the price of the production of world production exclusively depends upon the USA market, and that too with respect to energy consumption, nuclear generations, coal productions, gas productions, and fuel rate. So, all these things are there to predict the world oil price or oil productions, but the thing is that here we are restricting to 5 independent variables, and there is a high chance since all these 5 independent variables are connected to US economy, as a result the energy consumptions and nuclear generations, coal production, gas productions and fuel rate may have some kind of internal link. So, what will you have here? So, you will find out how long they are related to each other. So, technically in order to establish this, let us see the case. So, in the first instance, if you actually build the model, so we will have a system like this. So, y equal to function of x 1, x 2, x 3, x 4 and x 5, but there is a high chance that all these 5 variables may not be in the final setup because of this multicollinearity problem. So, if you could actually include all these 5 variables without multicollinearity problem, then this is excellent, but if that is not the case, so we will find out the scenario or the good models where more number of independent variables will be there and they are free from the multicollinearity problem. So, so as a result, so we will have a different kind of shapes through which you can actually pick up a particular items depending upon our requirement. So, ultimately we have a couple of structures so far as a multicollinearity is concerned. First all possible regressions, then stepwise regression. That means technically out of 5 variables, if you say all possible regression means it is y with all independent variables simultaneously. Now, the moment you will find the all these independent variables are not actually fit for the model building, then we will go for the stepwise case. So, where we will have a kind of structure that will take you to the case where it will be free from multicollinearity problem. So, that means technically so we have a structure called as a stepwise regression. So, it will go step by steps to check which are the important variables are good for this particular predictions, and that to avoiding the multicollinearity problem. So, stepwise regression has 2 options, forward selection and backward elimination. The forward selection process, you start with the most important variables, then the second most, third most, and every time so we have to check the model accuracy and the correlation among the regressor. Then finally, we will freeze a particular structures where all these variables will be there in the systems and that too have no multicollinearity problem. Similarly, in the backward elimination process, you start with the full model, then the most least variable which is not affected drastically. So, that will be dropped, then subsequently you have to drop one by one until you get a model which is actually good for the estimation, prediction and forecasting and without any multicollinearity problem. This is actually the last part of the game where we need actually final models which is free from the multicollinearity problem. But before that, what will you do? We like to check what are the ways you can actually detect the multicollinearity, how is the level of multicollinearity, what is the consequence of multicollinearity, then how to look for the solutions. Of course, this is one of the solution, but this is not the ultimate solution. So, let us see what are the ways we can actually discuss. Now, corresponding to this, if multiple regression problems where we have a dependent variable with the 5 independent variable. So, we have a following kind of modeling structures, y with single predictors, y with 2 predictors, y with 3 predictors, y with 4 predictors and y with 5 predictors. So, this is when we go for model design. So, you can have like this, but ultimately if you start with first to last. So, that means this is the single predictor with y upon x 1, y upon x 2, y upon. So, that means there are 5 such instances. Similarly, here if it is 2 predictors, then we have a couple of instances, 3 predictors we have also a couple of instances, 4 predictor we have a couple of instances and 5 predictor we have a couple of instances. That means, altogether we have all such possibilities. Then out of which only one possibility finally we will pick up to predict the world oil production subject to all these independent variables related to USA market. So, now how we can do that? So, let us see. So, that means technically before we go to this process. So, the stepwise process is like this a regress y with all these independent variables one by one, and you will find most important variable is the x 1 that is energy consumption, and then followed by the x 2, then x 3 and then x 5 and then x 4. So, like they have a different impact, they are not actually equal impact. So, this is as usual structure of the regression. You cannot find uniform impact of all these independent variables. Some will impact very high, some impact very low. So, likewise this is the reality. So, after knowing all these details, let us come to the multicollinearity problem again. So, it is the question of linear relationship among the regressors. So, and a game of independent variables. The relationship is linear in nature, multivariate framework. Then we are looking for the degree of associations. Then we will try to check whether the degree of relationship or degree of association between these independent variables are statistically significant or not statistically significant. That is how the multicollinearity come into the pictures to select a model which can be free from the multicollinearity issue. So, these are the possible shapes you can find in the real life scenario, and if you go through these shapes, this is the case where we have no multicollinearity, and this is the best, and this is low multicollinearity, and this is a little bit moderate, this is a high, and this is actually very high multicollinearity. So, when we call as all the correlation coefficients among the independent variables are 0, then that means technically you can have like this. If you say add another independent variable, then it can be like this, then it can be like this, it can be like this. So, that means they are completely independent, but now in this case you will find it is between y and x 2 x 3, somehow there is a slight relationship between x 2 and x 3. So, this is actually, this may be go ahead with the prediction because it has a low multicollinearity problem, but this case it is actually having high multicollinearity. So, you can create also very big ones like this. So, this is actually severe problems of multicollinearity. So, that means technically after plotting or looking like this, so you can guess what is the level of multicollinearity. Of course, we can quantify the level of multicollinearity problem by noting the correlation coefficient. Close to 1 is a high multicollinearity, close to 0 is very low multicollinearity. So, when it is close to 0, then this is good for the model building, and if it is close to 1, it is actually not good for the model building. So, likewise we will have the understanding, and then what are the actually regions through which you can actually expect that there will be multicollinearity. Sometimes as usual the variables are by default they are related to each other. Sometimes the model specification may be wrong. So, the sample selection may be wrong. Then sometimes there is a question of over identified model, and sometimes low sample size or excessive sample size may also create such kind of problem. So, we have to actually find out a optimal kind of an environment where we have the estimated model and which is actually free from all these kind of issues. In the first instance you have to find out the existence of multicollinearity, then you think about the regions and the kind of solutions. The regions of having multicollinearity is not so important, ultimately it is in the system. So, you have to clean the particular system, otherwise you cannot go ahead with the prediction and forecasting. So, what are the sources it is coming, that is not more important. What is important, check the level of multicollinearity and think about the solution procedures, that is more important. So, far as solving any engineering problems with respect to the prediction and forecasting. So, so this is one way of saying perfect multicollinearity. So, here you see x 2 and x 3. So, technically x 2 is nothing but 2 of x 3 is nothing but 2 of x 2. So, that means in this case, so x 3 equal to 2 of x 2 or x 2 equal to 1 by 3 x 2. So, that means technically a same data points are are repeated with different levels by multiplying 2. So, that means technically x 2 and x 3 are same. So, in the if you model with y x 2 and x 3 simultaneously, then you do not find any result at all. So, sometimes if you use any software will give you some kind of error signal. So, since it is actually very easily you can detect or you can recognize. So, in the first instance either you keep x 2 or x 3, but you cannot keep actually x 2 x 3 simultaneously, because this is the case of perfect multicollinearity. So, you have to remove any one of these two variables. So, now mathematically without knowing x 2 and x 3 you can drop either x 2 or x 3, but theoretically or any kind of real life problem, engineering problem. So, before dropping x 2 or x 3 you have to think which one is more important, which one is more relevant to this particular problem. Then you can keep that ones and the other one you can actually. So, that means prime importance you can. So, the level of inclusions not only through statistical criteria, but also theoretically you have to check the prime regions or prime impact both theoretically and statistical, and then finally you have to freeze as per the particular requirement. Ultimately the structure will be like this, and so this is actually the case perfect multicollinearity case. And in that case, if you establish linear relationship, then then it will be declared that both the variables are linearly dependent. So, as a result, you cannot actually use this model for the case of model building or model estimation. Similarly, if 5 explanatory variable, the structure will be like this. Then you check whether these coefficients are statistically significant or not. For instance, if you have actually 5 variables, you can connect actually x 2 upon x 3, x 2 upon x 4, and then check these coefficients are statistically significant or not. So, that means knowing the existence of multicollinearity, either you can apply covariance or correlation or even regressions. These are the standard structure through which you can detect. Of course, at the upper levels some checks are there which can give you little bit hint to know the existence of multicollinearity problem in the estimation process, and this is the case of consequences. When there is a multicollinearity problem, so your OLS estimators are not actually blue. That is what we have already discussed, best linear unbiased estimator. So, usually in the presence of multicollinearity, your standard error will be very high and make the coefficient indeterminate or something like inconsistent while building models or use the model for the prediction and forecasting. So, so ultimately multicollinearity is a serious problem in the case of regression modeling. So, these are all the case of difference, and usually when we try to test the particular variable, the variability part or the standard error of these particular estimators will be very high. As a result, the t statistic of this coefficient will be indeterminate. As a result, it is clear that having multicollinearity, you can get the model estimator model a reliable one. So, you have to be very careful how you have to deal with this situation. And there are lots of other indicators through which you can check the multicollinearity. One of such indicator is VIF, variance inflation factors. It starts with 0 to 1. So, it depends upon 1 by 1 minus r squares, that is the coefficient of determination. And in this case you will see here the kind of structures, the range. It will start with simply a r square equal to 0, VIF equal to 1, and r square equal to 0.5, VIF equal to 2. So, that means high variance inflation factors. So, it will give you high multicollinearity problem. So, this is actually it's a kind of perfect and severe multicollinearity problem. So, if you close towards r square 0, so then there will be less multicollinearity problem. So, this is how actually you have to check. That means, technically the multicollinearity problem can be checked through VIF without knowing the intercept, etc. So, this will give you little bit signal, but ultimately which particular variable will be having or which particular pair will be statistically significant and producing high multicollinearity. For that you have to go either through correlation matrix or simple linear regression or covariance approach. So, ultimately this clears that this happens for r square 0.9. So, that means technically VIF values that exceed 10s are generally viewed as evidence of existence of problem of multicollinearity. That means technically what we have already checked here. So, this side onwards. So, you have actually severe multicollinearity, then degree of multicollinearity is slowly low and this is very low, and when VIF equal to 1, then there is no multicollinearity problem. So, when it crosses 10, it will have a severe multicollinearity problem, and this is the real life examples, and we have a different kind of setups. In this case, there are 3 such instances. Of course, we will solve a particular problem through subtiers, but in the meantime, if you look here, then in the first model VIF is coming 6565, and here VIF is 2856, here it is actually 297. So, that means different level of VIF factors, but in all the cases the model is actually having multicollinearity problem. This is the clear cut signal, and of course, you can actually check through various ways to justify the authenticity of this particular problem, and but ultimately if the smoke is coming in one particular mechanism, so obvious it will also appear in other such instances. So, likewise, so you can be very careful how you have to deal such scenario, and okay. So, far as a consequence of imperfect multicollinearity is concerned, so estimators will be efficient, consistent. So, what will try to do? So, we like to actually bring a situation where the standard error or variance of these parameters will be very low. As a result, the statistical significance of the parameter will be accurate or consistent, and then it will be statistically significant. So, ultimately we have to bring such kind of an environment. Even you would like to drop some variables, does not matter, but ultimately your model should be free from all kind of obstacles. So, for the detection criteria is concerned, so we have already highlighted the covariance mechanism, correlation mechanism, regression mechanism, then the VIF mechanism, and some of the other criteria like here. Very simple way to check the model and give the answer. So, that means sometimes what happens, there is an indicator called as a coefficient determinant R squares and the beta coefficients, that is the coefficients against all these independent variables. So, the model requirement is like that, or you can say that the model is absolutely okay, fine for the prediction and forecasting when R square is high and in the same times all the parameters are statistically significant. That means, all the beta coefficient will be statistically significant. So, now if R square is high, few parameters are statistically significant and others are not significant, then this may be due to multicollinearity problem. Reverse is also true. So, when most of the variables or parameters are statistically significant and R square is low, so this is also actually a bad signal. So, that means the signal will be very good and green. So, when R square is high, most of the variables are statistically significant, or vice versa is also true. When most of the variables are statistically significant, R square should be very high. So, if that is not the case, then this will be create a multicollinearity problem, or else if low R square, then the significance of the parameters will be at the low levels. For instance, out of 5 only 2 or 3 can be statistically significant, and that too may be at the 10% level. But when most of the variables are statistically significant and R square is not very high, then this leads to a problem of multicollinearity problem. Likewise, okay. So, what I have already mentioned. So, you can regress one independent variable with the rest of the independent variables, you can use simple correlation, you can use partial correlation. So then you can find the level of correlation. That means high pairwise correlation among the regressor will give you the multicollinearity issue. Then okay, so this is what we know partial correlation, and this is what the auxiliary regression. So that means from this auxiliary regressions you can find out R square, and then you can connect with the BIF also. So that means ultimately we have already highlighted a couple of different ways to check the multicollinearity and to validate the estimated models and check whether they are in favor of the Wallace mechanisms or they are favor in as per the particular model requirement. So through eigenvalue and eigenvector also you can check the multicollinearity problem. So since we have already mentioned that all these independent variables are linearly independent. So that means if you calculate the correlation matrix, if they are linearly independent, then their correlation matrix or value of that particular matrix will be 1. So that means that will take you to the unit matrix. But if there is a multicollinearity problems, then this particular matrix cannot be transferred into the unit matrix. So this gives the signal that there is a somehow multicollinearity problem. That means technically there is a linear relationship among the regressors. And against there is a component called as a condition index, which is actually square root of maximum eigenvalue by minimum eigenvalue, and when the k moves in between actually 100 to 1000, then it is moderately exist, but when it crosses 1000, then it is a severe multicollinearity, like BIF. Once it will cross 10, then this will be actually having severe problem. If it is under 10, then it will be having less less problem for the prediction and forecasting. So this is actually we have already discussed this BIP, and that means technical tolerance factor. So the 1 minus R square is the tolerance factor. So BIF is actually calculated by the 1 by tolerance, and tolerance is the tolerance exactly equal to 1 minus coefficient of determinants, that is R square j. So now the question is how to actually detect, solve this particular multicollinearity. We have already gone through several ways to detect the multicollinearity, get to know the consequence, then we are looking for the solutions. And so far as the solution is concerned, there are multiple solutions we have, and once you have to pick up which one is good for your model building and model estimations, and that to predict any engineering problem and the kind of forecasting. So one way to solve the problem is you can simply go by increasing sample size or decrease the sample size. Variety of ways actually you can check, then you input you can change, then you will find output change, then you compare different levels of output and fix a particular model where the problem is not at all there. Then as simple other way is drop the collinear variables and then go ahead with the prediction and forecasting. But dropping a particular variable is not a good strategy. For instance, if that particular variable theoretically is very sound and having strong impact, then you cannot just drop the variable. So you have to find out alternative ways how to keep that particular variable, and that to the model is free from multicollinearity. Then sometimes we will go for variable transformations by fast different transformation, log transformations. By that way, so the existence of relationship may be little bit compromised or reduced, and you try to increase the sample size, and you can for cross sectional modeling you can bring different sampling, so that it will not create any kind of such problem. But in the case of time series data, so the existence of relationship will be always there, because the data are actually well connected with the time series. That is how the consistency. So somehow there will be relationship, but that relationship should not be statistically significant. Then sometimes you can actually structure the data with high frequency. In fact, that is how the kind of data restructuring is required. Either you go for data transformations or somehow you can do the labeling. So, instead of annual data, you can go for monthly data or weekly data or quarterly data. Some of this can give you better pictures, and the results will be also coming more accurate as per the model requirement or the kind of prediction requirement. And sometimes we can use different techniques like factor analysis, principal component analysis, because these are the technique we will usually use when there is a multicollinearity problem. So, usually factor analysis is applied when the structure is k greater than n, that means number of variables is larger than the sample size. So, we use factor analysis to transfer such kind of an environment. That means, instead of using more number of variables, we try to use few number of variables with some kind of restriction and the kind of mechanism, and these few variables will be by default free from multicollinearity and other errors in the system. But if there is means this is typically applied when there is a more number of variables in the system, but if it is a few number of variables are in the systems, then factor analysis may not be used to solve this multicollinearity problem. In that case, you will look for other different ways, like data transformation, increasing sample size. Even if you can change the functional form, then you can sometimes drop the collinear variables after knowing the correlation among these regressors. If there if a particular pair is coming actually very significant, for instance let us take close to 0.99, it is better to drop a particular variables instead of looking for other way of solution. So, likewise we have a different kind of atmosphere, and then last but not the least we can use actually and the stepwise regression. So, stepwise regression is the last step where we will solve the multicollinearity problem, but in the first instance you try to apply all these possible techniques by dropping collinear variables, then increase the sample size, change functional form, transfer the data into high frequency data, then increase sample size, decrease sample size, apply different methods like factor analysis, apply different structure like ridge regressions. So, these are all various ways you can solve the problem, and finally, if you could not, then you start the stepwise regression. Stepwise regressions, so what I have already mentioned, it has a backward operation and forward operation. In the forward operations, you start with the most important variable first, and that is the most important independent variable which influence the dependent variable. Then you find out the second most important, then you check the reliability of the model every time, then you have to stop where the reliability will get affected. For instance, the starting procedure is for this problem y equal to function of like this, what we can do, this is a full model y equal to function of x to x 5, then you check you run the model and check which particular variable is having more high significant part. Then in the first step of stepwise, so y equal, let us say this is nothing but x 1 only. So, you start with x 1s, then see the beta 1 coefficient value and the statistical significance and the r square value, and followed by f statistics, and then you find out another variable which is a high import after x 1, then let us say it is x 3. So, then in the next models you start with f x 1 and x 3, then you check beta 1 coefficients and beta 3 coefficient and r square and f. If beta 1 coefficient, if statistical significant, beta 3 significant, r square high, f significant, then this will be good models, you can reject this one. Again you proceed with another way. So, now x 1 and x 3 is in, so x 2, x 4, x 5 is remaining. So, again you to enter x 2, then check the kind of structure. If again they are improving, then you keep the latest one, then remove the previous ones. If after introducing x 2, if you are not means x 4, if you are not getting good, then you can reject these ones. Then what you can do, you can start with x 1 x 3 with x 4, then you check the environment whether it is good or bad, then again you compare and fix which one is good for you. So, likewise you can continue till you find a kind of structure which is actually good for the forecasting or prediction of the any particular engineering problem, and at the same times it will be free from multicollinearity problem. And in the backward sides you start with full models like like this, then what will you do, you try to drop one after another variable. For instance, let us say x 5 is the target variable, which is actually having very low impact, and that you can get to know with the coefficient of that x 5 and the true significance of that particular variable. So, now in the first step of backward elimination, so you drop that variable, then you run the model and check the reliability of the model. So, obviously, the second step, the estimated model will be good one compared to the previous one. Then if it is not, if it is good, then you can keep, you can reject the previous one. Then finally, you come to step 2, where another variable can be dropped. So, you check which one is the least impact again, then you drop that variable, ensure that remaining of the variables will be statistically significant, R square will be high and F will be significant. If that is the case, you can go ahead with that models and reject the previous one. So, likewise you will continue, then finally, you will reach a optimum point where your dependent variable will be predicted with a couple of independent variables which are free from multicollinearity problem. That is what the requirement of OLS mechanisms, and it is in favor of the OLS assumptions, and this is what actually one way called as diagnostic check of model building. So, one of the diagnostic check which you can carry, whether it is a cross sectional modeling or time series modeling, is to see whether the relationship among the regressors or independent variable or explanatory variables are not related or correlated to each others. If that is the case, so the particular model cannot be follow the blue theorem and cannot be used for model estimation or model predictions or forecasting. So, what will it do? So, every time while doing the kind of estimations, be careful to how to check these kind of relationships. So, at the end of the day, you must have a estimated model which is used for prediction and forecasting, that is exclusively free from multicollinearity problem. After knowing all these criteria, the consequence, the kind of detection, the kind of solution, I am very sure that once you start a particular problem, so you will finally reach a particular point where the estimated model can be very efficient to predict and forecast, and that too with the problem of multicollinearity. But only multicollinearity is not the diagnostic solution or diagnostic check. There are couple of other problems are there, like heteroscedasticity, autocorrelation, and some of the other issues. So, which we will discuss in the later stage, but in the meantime up to this stage. So, once you go for the multiple regression or multivariate regression, so be ensured that the final estimated model should be free from multicollinearity problem, that is the existence of linear relationship among the regressors. If that is the case, means the model is free from the multicollinearity, you can go ahead with the prediction to solve the particular engineering problem without any errors, and because it is practically having the model is reliable and that too free from multicollinearity without hinting the other components, but ultimately end of the day you have to check all these diagnostics, starting with the multicollinearity, heteroscedasticity and autocorrelation. But up to this point we are very much sure that how to fix a particular model which is free from the multicollinearity problem. In the next class, we will discuss the other diagnostics and check the reliability of the model as per the particular requirement. With this, we will stop here. Thank you. Have a nice day.